Good, we're ready to restart. Let's start with a little quiz that will also make a transition to other stuff we'll need. Here I'm showing a problem P, which looks very complicated, but it's the problem we know from our toy example. Minimize a cost function subject to the constraints that the loads are in some intervals here. Or at least it's a small variant of what we saw before. A and B are also some variants of it. A differs from P by saying that there is a quantifier here in front of L1, L2, L3, and B differs only by another quantifier. This means there exists, so for at least one value of L1, L2, L3 in this sets, then we have the constraint, and similar for B. B with the other constraint, with the other quantifier for all values here. So we have three problems that differ only by the presence of quantifiers in front of some of the variables. Right? And the question is, which of the two problems A and B, or none of them, is the same as problem P? And we have a tie between A and B. So half-half, right? And another part says both. The correct answer is A. Only A is the same as P, right? Let's reason about this. I mean, first, it's not the same as B. In A, we say, find a set of variables, L1, G2, G3, L2, L3, that satisfies all of those constraints and minimize this. So I have to choose L1, L2, L3, G1, G2, G3, G2, G3. Here it is subtly different. I'm saying I'm choosing only G2, G3, but the constraint is that there exists L1, L2, L3 that satisfy the constraints here. Right? And since L1, L2, L3 do not appear in the cost function, as we will discuss in a minute, this is the same as that. Right? Saying find some control variables G that minimize the cost, subject to the constraint that there must be a feasible way of choosing L that satisfies the constraint. Then this is the same as saying choose G and choose L. Right? And it's not the same as this one, because here we're playing a game where we choose everything. We choose G and we choose L. Here it's not the same game. We choose G, but someone else chooses L. We're saying for whatever value of L, the constraint must be true. So it has to be true for all possible values of L, which means including values that we don't like here. So B is certainly not the same as P, and what is a bit less obvious is that A is the same as P. In general, we have this. Whenever I have to minimize, I have an optimization problem. This is a simplified notation for our P, problem P. X is the G, and Y is the L, right? So here I can write it in this form, minimize over the variables X and Y, some function of X only, such that X and Y satisfy some constraint. A shorthand notation for satisfying the constraint is to say they belong to some set S. Of course, S is a complicated set, but it makes the description short. Well, this is the same as that. Minimize f of x subject to such that there exists y such that xy is in S. Remember that when there is a quantifier, a statement, the output value of a statement where there is a quantifier does not depend on the value of y. So this statement here is a statement on x. I'm saying x is such that I can find a y that makes the constraint true. It's true or not depending on the value of x I have chosen here. So I have formally two different optimization problems. One that depends on x only, here one that depends on y. But they are the same. Intuitively, it's fairly clear. If you're not convinced by why it's clear, in the next slide that I will post as soon as the lecture is over, which is in the solution files. There is a formal proof of that. But the important thing is to have the intuition. This is the same as that because y does not depend on the objective function here. And this is a very common thing to do. Here I'm saying I add supplementary variables to this problem by putting the y into the optimization variables here. Right. And the other thing that's, of course, to be aware of is that if we put for all instead of there exists, we have a radically different problem. Here we're saying choose an x, the best x, such that I could also choose a y that satisfies the constraint, which is the same as choose an x and choose a y. Right? If I put a for all, that means choose an x so that whatever the y is that is chosen by your adversary, the constraint is satisfied. Voila, so we will use that kind of transformation in the rest here. Now there is a variant to what we have seen so far, which is more risk-averse than the choice we did. And it shows up here in the choice of the optimization costs that we take. In the previous hour, we took an optimization cost, which was the expected value of the cost in the average regarding, with respect to the unknown value of the disturbance. This is what we did. And I repeat what I said an hour ago. It makes sense if what we will be paying is the average, which is what is true if we do that repeatedly. If we do that every hour during a year, what matters is really the average, in particular if we receive the bill at the end of the year, because what we'll pay is the sum of the costs, and the sum is equal to the average multiplied by the number of costs here. So what will matter in that case is what we saw before. If we do it only once, then the things might be different, right? If we do it only once, we want to play u, and we will pay something, which is c of u and the result of the disturbance. Perhaps we're interested in the average, but also we don't have so much money. We think that if the value becomes very large, then we might be in trouble. It's like if you have to buy an airplane ticket, and imagine you have to take a decision when to buy it, and assume you have to pay just when you come to the door. Right? No, nobody would like it, but assume you would do that. But you say in average, if you do that, the price will be very low, but there is a risk that it's very high. And perhaps you would not like it, in particular if your budget is very short. So this is called risk-averse optimization, which is also called robust optimization. Robust optimization is when we replace the expected cost by the worst case here. We don't want to minimize the average, but the worst case. Of course, as you can imagine, we can do combinations of trying to minimize something that accounts for the average and doesn't lead to too high maximum value, but that's easy to combine. What we will see, what are the techniques to handle a case where we want to do this. The only difference with respect to what we did before is in the cost here. The cost becomes the mean over G2 and G3 of the max over L1, L2, and L3. Mean and max are like brothers and sisters. They don't always play well together. So the mean and max it's not the same as max and min, for example. So we have to keep it in this way. Right? If we have mean of mean, that's very easy. Right? The mean of mean is the global mean. If I take the minimum of f of x and y, I can first, for a given y, for any y, find what is the x that reaches the minimum, and then find the y such that for this x that reaches its minimum, the global thing is minimum. So we can do it in any order when we have mean of mean or max of max. When we have mean of max, then we have to be careful. They don't match easily together. So we have to keep it like this. But we have seen a way to get rid of this, right? We have seen already that a max of something can be represented by adding supplementary variables for every max. Here I call epsilon the max here, and saying minimizing the max is the same as minimizing epsilon, where I add the constraint that epsilon is larger than the value u of d for any value of d here. Because we have seen that if you want to minimize epsilon, since epsilon is an independent variable of all the rest, the only place where it occurs is through this constraint. For a given value of u and d, the value that will minimize that is the max of all those things here. So when we minimize something that has a max, we can do this. This we saw last week here. Well, at the expense of adding this epsilon here, we have a standard problem of the nature that we saw a minute ago. So we have added variables here, and we have robust constraints. Now epsilon is one of our control variables here. Here is what it gives for the case we saw here. We have now to add epsilon as the control variable. So we minimize G2, G3, such that then, well, epsilon is larger than the cost, but this, of course, has to be true for every L1, L2, L3. So we have the same problem as we had before with the G1, G2. We have to make it robust by solving, by using the same technique as before. We put all the L1 on the other side, all the epsilon on the other side, and we de-robustify the constraint using the same technique as we saw an hour ago, right here, which will give this here is, once I have de-robustified, I have L1, L2, L3 that are gone away. They appear through those parameters here. So of course I have had to solve 10 or 12 supplementary optimization problems to get to that step. So I've already solved quite a number of optimization problems to get there, and I still haven't found the solution to my problem. But now I can solve it, and that will simply give me the solution here. We'll not dive into the details of it. We'll come back next week to what it means to do worst case versus average case. Yes, the question. Yes, well, it's a typo. Of course, it depends on the values of uncertainty. Yeah. So this is a typo. This is when I take the very large uncertainty, then this one is non-feasible, of course. We find the same constraints as we had before for the part that do not have epsilon. It's exactly the same as before. The part that contain epsilon are additional thing here. So the feasibility constraints are exactly the same as before. What do we expect if we minimize the worst case cost? Will we be more conservative, less conservative, or the same? In general, we will be more conservative because we look only at the worst case, and depending on the specifics of the problem, the worst case may lead us to taking decisions that are good for the worst case, that result in lower costs for the worst case, but that are not necessarily good in average. Here. We'll come back to that topic to save time. I will not dive into it now because we will have exactly the same story in the demand response module, where this is also the same issue. So we'll look at it in more detail now. What we will do now is a more interesting solution to the feasibility problem we saw before, which is feedback. Whenever we have a problem of this kind, we saw that it's very easy to make the problem unfeasible, and it's very easy to understand that if you have to choose in advance something that will work in all cases, you have to be very conservative, and it might be that there is no single fit-all solution. There might not be a solution that works in all cases. What do we do if that happens? Well, we adapt. That's what we as Homo sapiens are very good at. We're not good at any conditions, but we're good to adapt. So in summer, we have certain clothing. In winter, we have other ones. Of course, we don't pick a case with all the garments we need for any season. The same is true when you run a grid. When you run a grid, you may want to adapt by changing in real time the set points here. So in the exercise we saw before, we had some uncertain loads and we needed to fix G2, G3 such that whatever happens, G1 will be able to balance and the flows on the line will not exceed the limits here. And we've seen that if the variability is very large, that may cause a problem. But if the variability is very large, perhaps we will detect that this happens. We will see that the power flow is too large and we could change the set points of some of the generators. Of course, that will require some equipment. We need a controller on the generator. We need a sensing system that's able to sense what has happened. And then we need a control law to say, based on what happens, how do you change the set point here? So a very simple thing to do is to use linear control law. So here is one example. It's called affine disturbance feedback control. Control because we're controlling the state of the grid. Feedback because we assume we measure the disturbance. How can we measure the disturbance in that case? Measuring the load. Well, if we have power meters in the devices, then that's something we can do. And then we need a communication infrastructure, a smart grid. So that's a first example of an intelligent grid, a smart grid, that if we measure the load, then we can send the instruction. In this case, I'm assuming only generator 2 is intelligent. So generator 2 is, for example, a fuel-based generator, is able to adapt its power, or it's a PV plant that for which we can curtail some of the load, and it's able to adapt its power according to a control law. To make things simple, we make the control law linear, or more strictly affine. Affine means linear plus constant. So here it's linear with respect to the disturbance. So the output of the control law is the control action, G2. And then we need to specify parameters of the control law, which are the parameters of the linear dependency, the slope and the offset, U2 and V2. That becomes also control variables now. So instead, when I do day ahead my programming of this grid, what I have to choose is not G2, but is U2 and V2. I choose those two things. In a simple case, if I want to be completely non-adaptive, I can set V2 to 0, and then I choose G2, which is a fixed value. This is what we did before. But now I'm allowing G2 to depend on V2. If I want a small dependencies, I will put a small value of V2. So my problem is now find the values of G2 that will be implemented in the controller here. So of course, assume I have a controller in this generator, and as mentioned before, that means we have a smart grid here. So it's called affine disturbance feedback control. That's a very classical mechanism in control theory. Disturbance because it depends on the disturbance, affine because it's an affine function here. As you can imagine, as soon as we have feedback, we have better control of the system. Yes?
Is V2 here the angle, or?
No, V2 has nothing to do with the angle, nor the voltage magnitude. It's just a parameter. It's in red, so it's a different one. Yes, I should have given a different name to it. Yeah. The angle is still theta 2 if we do the DC approximation here. So we continue with the same assumptions on the cost. We assume the costs are linear, so what we care is about the forecasted values. Now, if I have chosen U2 and V2, then the forecasted value, now in the sense of the randomness of the nodes, will be exactly this. But the actual value, G2, will be the same with the true value. So the difference between the actual value and the forecasted value will be V2 times the difference in the loads. So we will adapt. This shows exactly how we will adapt the margin in generator set point 2 as a linear function of the variation of the total load. Here. I'm doing the DC approximation to run this system. So a formulation of this problem. The control variables now are G3, that remains a fixed generator that we assume is not controlled by our smart grid, and U2, V2, which are the parameters of our generator G2. So the disturbance is as before, and the state is as before, theta 2, theta 3, and G1. The expected cost now becomes a cost that depends on G3 and U2, V2. Now I put the numerical values for the expected value of the loads, and that gives me this thing here. That's the expected cost of my grid when I have U2 and V2. Remember that if V2 is 0, we have exactly the same problem as before, where U2 was simply G2. The constraints result from replacing G2 by its function of U2 and V2, so it's a bit more complex to write. This is what we obtain here. For example, if I look at constraint on the line 1, 2, we obtain something that depends on the power flow that depended itself on the injected generation G2 that is now replaced by its expression as a function of U2, V2, and L, the disturbance. In abstract form, this is how we can formulate such a problem. We have to minimize a function which is here linear of our cost of our control variable U, which is now U2, V2, and G3, subject to constraints that are linear and must be true for all value of the disturbance, but there is here a nasty term that comes here which is not linear, which is bilinear. It depends, it's linear in D, in the disturbance, and in the control variable, but it globally between the two, it is quadratic here. It depends on the product of the two here. So we have a general problem of that nature here. Right? If we did not have this, we know how to solve it. We put the D on the other hand, we replace the right-hand side by taking the minimum of the right-hand side, and then we're done. Now we have this term here that makes it a little one notch more complicated. Let's see how we can solve it here. So we have the generic problem to solve. Now I forget about my grid and I go back to optimization theory, and I say I have to solve a problem of this form, which is given here. And D is a disturbance, U is a control, and the disturbance and the control are related by a common term in the constraints here. So let's start with the same approach as before. I will put on one side of the equation all the values that are here, right? Or I put all the U on the other hand, and saying that U is larger than all the values here is saying that U is larger than the max. An hour ago I had put the D on the other side, and then U would have to be less than, so it will, all values, it will be less than the mean. Here I put it on the other side, but that makes no difference. So we have to solve this problem here. Now the difference is that this problem depends on U. An hour ago it was independent of U. So I call Pj of U. J is the index of the constraint I have here. For every constraint J, and for every value of my control variable, I have an optimization problem to solve. And if intellectually I can solve it, of course we have a problem because there's U in it. So, but we'll see how we'll get rid of this cyclic dependency. If I can solve it, I would find P star J of U, its optimal value, and then the constraint that was here is the same as that. I had obtained this by putting the terms in U only on the right-hand side, and this is saying that the right-hand side was larger than all values of over D, then it's the same as being larger than the max. So at least in theory, it is solved here, because now this is a function of U only, and I have a constraint that depends only on U. Now, Pj star of U, the problem is that I don't have a closed form expression, apart from very simple cases, but in general, I don't have a closed form expression for Pj star of U. So if I had a closed form expression, then it's done, but in general, we don't have that. But there is a silver bullet here, which is the use of duality. We can use the dual of the problem to solve this. You have seen duality in the exercise last week. So we have seen that when we change an optimization problem to its dual, we change min into max. We'll come back in a minute to the specific case of linear problems. Linear optimization problems are particularly simple to analyze from a duality viewpoint. It's very simple to write the dual of an optimization problem. It's hard to remember it by heart, but it's easy to do. This is what I did here. I looked at the dual of the problem Pj of u. So Pj of u is a linear optimization problem, this one. Again, I'm doing this technique of divide and conquer. I look at one problem at a time. I forget about my big problem. My problem is very complicated, but I look now at only one part of it, this problem, and my problem is write the dual of it. That's a linear optimization problem. Once u is fixed, bu is simply a vector. So with respect to d, it's a linear optimization problem with a cost function, which is bd plus d times that stuff. So it's a linear function of d subject to a constraint on d. We will see in a minute that there's a catalog of ways to write the dual of a program. The dual of the program Pj is what I call dj of u, is exactly this. Is the minimum over the optimization variable lambda j, where lambda j has the same dimension as c. C was the right-hand side of before, subject to those constraints here. Right. What is important is not the specific form of the dual, but is the fact that we've replaced a max into a min, which is a very big difference here. Because the condition we had before was that. The condition of u was that u, this function of u, is larger than this here. But now if strong duality holds, which will hold for all linear problems that are feasible, the optimal value of a problem is the same as the optimal value of the dual. That's the main interest of duality. So this is also the optimal value of this problem here. But this problem is a minimum. So this is saying that this quantity is larger than or equal to the minimum value of Ct lambda j. Right? Now, what does it mean to be larger than the minimum of something? Well, that's a question that we almost addressed a minute ago. When we did the quiz, we saw that saying that an expression is less than the all values for all is saying that it's less than the minimum. There's another thing that we could say, which is here, saying that an expression is less than at least one of the values of f of d1 is the same as that the expression is less than the max. Right? It's fairly obvious. The only non-obvious thing is to know that this equivalence occurs. You can remove quantifiers by introduce min or max. Now you have to be careful and pick the correct one. Here, if I'm saying expression something is less than one of the values of f of d for some d, then being less than one of them means that you are less than the larger of all the values here, which is the max. Right? If you would put the min here, that would mean that you're less than all values here. Being less than the min means being less than all. Being less than the max means being less than at least one of them here. That's the main trick. That's the main trick we will use here. So once we have reached that point here, so this trick, together with the use of duality, tells us that once we've transformed a problem where we have min instead of max, it tells us that it is the same as saying u must satisfy the condition there exists a value of lambda j such that this expression is larger than the value which is the objective function Ct lambda j. So there exists a lambda j such that this is larger than that. And the lambda j must satisfy the constraints that are before. Right. And then the last step here is to say, saying that in an optimization problem I add a variable with the quantifier there exists is the same as adding the optimization variable to the set of optimization variables. This is also what we did just a minute ago when we saw that problem P was equal to problem A. So saying that there exists a lambda j is the same as adding lambda j as one optimization variable and satisfying and putting the constraint here. So lambda j must satisfy all the constraints that are given here plus this one here. Now I do it for all of the capital J constraints. So for every constraint, I add one vector that has coordinates the same as dimension as C here, and then we obtain this thing here. So at the cost of adding potentially many optimization variables, I have transformed the problem that was a robust problem with quantifiers, embarrassing quantifiers in the constraint into something that does not have it here. When doing that, we used the dual of a linear program. So in order to do that, we need to be able to compute the dual of a linear program. That's very easy because you go to the Wikipedia page and this is what you find, essentially. So you will find that if you write your primal problem into one of those three forms, there is a canonical form to write an optimization problem, but very often it's convenient to differentiate between different forms, in particular whether we have non-negativity constraints on some of the variables. We could say non-negativity constraints can always be included in the matrix B, but for optimizers it makes a difference. If you put them separately, usually the size of the problem reduces. So if I take this optimization problem, here is its dual here. This is what we had in the example I showed a minute ago. Duality works both ways. That's why it's called duality. So the dual of the dual is the primal. So this works both ways. The dual of this program is that one here. So with this form, you have here a catalog of 6 optimization problems, and in principle, every problem you have should fit here. Right? Yes? Yes, sir?
If you can just go back to before. Can you? I haven't really seen the benefit of using duality. So we don't have non-negative constraints. That's the...
No. The benefit is to be able to address this here. I don't know how to address this, right? I have the quantifier. I have a constraint. I must say my U must satisfy this constraint. And for a given U, I can compute this by linear programming, but I don't know U. So I need a way to explain that in the constraint. This is an implicit constraint. I need to make it explicit if I want to call a standard optimizer. Right, so that's the difficulty. This, we don't know how to express it. In the general case, there might be simpler cases where you can express it and you don't need duality, but in the general case, that's the standard approach that always works. In the previous case, when we did not have this term that combines both, the P star was independent of U. So I solve the problem once for all, and then I'm done. But now that's the problem. It depends on you. So in practice, we will need to write the dual of a program, and it can be done by simple inspection. Still, by curiosity, we could wonder, where does it come from? And with what you should have done last week, it should be very easy to understand. The Boyd and Vandenberg's theory solves everything that is solvable today. So let's apply it. For example, trying to compute what is the dual of this program. So I use the textbook method. I first write it in the standard form. So the standard form makes it a minimization problem, which is minus AX. And I must also have inequalities less than 0. So this is my inequality value here. Since there is no equality, the Lagrangian has only the lambda and no new variable. The Lagrangian is this, which is gives that. And I need to compute the dual function and its domain of definition. So the dual function is the same minimization in this problem here, where I've removed the constraints, so I have to minimize this here. Now it's both very easy and very hard. It's very hard in the sense most of the time the solution doesn't work here, because I have to minimize with respect to x. Now x is unconstrained. It's a vector that is in r to the power n for some n, so it can be negative or positive. If I minimize a linear problem in x, in general the solution is minus infinity, because x is unbounded from above. So the only way, and we want the domain of definition for this Lagrangian theory, which means the values for which it is bounded from below. So I must found condition under which it is bounded from below. And the only way it can be bounded from below is that the coefficient, the linear part here, is 0. So it must be 0. The coefficients are this, so that gives this condition. This must be 0. So that makes the problem very easy. The constraints on the dual variables lambda that make the dual function bounded from below are this here. And now what is g of lambda? Well, it's very easy, because now it's a constant, minus lambda transpose b, which, by the way, is the same as minus b transpose lambda, because this is a number. Lambda is a vector, b is a vector. It's the inner product of lambda and b, which is the same as the inner product of b and lambda. In general, for two matrices, if I change the order, I obtain the transpose of, but if it's a number, the transpose of a number, a one-by-one matrix is the same here. So the dual problem of this is maximize the objective function subject to this constraint here. Now I had to transform my problem from max to min, so I was minimizing minus the objective function. If I want to recover the original problem, I have to minimize b lambda such that those constraint here. So this is why the dual is this here. So writing the dual can always be done in this form, which is very systematic. Of course, if you do it for linear programs, and it's been done zillions of times, you can simply look up this, and as a homework, you can take any of the 6 problems and try to redo it, and you should find what we've found here. And we know that strong duality holds if we need conditions, and one of the conditions is, for example, if the constraints are affine, which is always the case here, and at least one of the two problems is feasible. So if at least one of the problems is feasible, and typically feasible means that the set of constraints are consistent. We have seen a minute ago when we do robust optimization, we may write in equations that are not non-consistent, then there's no solution. But if any of the problem is feasible, strong duality holds, so the optimal value of one is the optimal value of the other one, right? Which is what we need to solve our affine control feedback system here. So in general, if I have to solve that, that's exactly what we've seen a minute ago. This will give, by introducing the dual, it removes the for all, replaces by there exists, which is the same as adding optimization variables. Let's do it for our toy example. For one of the constraints, the first constraint, which is again saying that the generation of the slack bus must be non-negative. So I first isolate the elements that depend on the disturbance only, and I obtain this writing here. U2 plus G3 has to be less than that for all value of L1 and L2 here. This could be solved explicitly in this case, because it's a very simple optimization problem. It can be solved explicitly. It depends on the sign of 1 minus V2. If V2 is larger than V1, than 1, then this is negative and the mean will be reached for the max. If V2 is less than 1, the mean will be reached by the mean. So you will have an optimal, the P star of U, the optimal value, has a quasi-closed form. It has a closed form, but with a condition. If V2 less than 1 something is V2 larger than 1 something else, which can make it tractable. And then you can do it for the 12 constraints that you have in your problem, and then you will have a formulation. Or you use the systematic approach, which is better in the sense that it saves human brain cycles, because all we have to do then is apply systematic things. So here I have to compute the dual of the problem that we have here. So I have to write it in the form that is here. So I write it in the form minimizing a linear function of y subject to linear inequality of y, and the solution is given there. So what is my matrix capital B, what is my vector B, and what is my optimization variable? So here my optimization variables in this problem are the disturbances. My vector B is this, because I'm minimizing 1 minus V2 L1 plus L2 plus L3. And my constraints are those. So we have a big matrix here that I need to write. The constraints are L1 between 0,9 and 1.1, which I can express L1 less than 0,9 minus L1 less than minus 1,1. So that gives the first element of this matrix. Those are the constraints on L2. Those are the constraints on L3 here. I have to transpose this matrix, and the transpose of the matrix will give me the linear constraints on the dual variables. The dual variable I call x in my catalog of duality. Here I call them lambda 1, because that's the first constraint. The 1 is because of the first constraint. And then I minimize ax. So a is the right-hand side, which is this vector here. So I minimize 0, 9, lambda 1, 1, etc. That's my optimal value. Subject to the constraint of the transpose matrix. So the transpose matrix will give 1 minus 1, but I read them by row instead of by column. So that means lambda 1 minus lambda 2, lambda 1 minus lambda 2, is equal to B, the vector B, 1 minus V2. So lambda 1 minus lambda 2 is equal to 1 minus V2. And the same for the other two. So those are my constraints. And the duality tells us that the lambda 1 has to be non-negative also. So this is the dual program I have here. Of course, if I solve this, I will obtain the same value as before. The optimal value of that will depend on the sign of 1 minus V2. That's easy to see why. If 1 minus V2 is non-negative, V2 less than 1, then we see that lambda 1 must be larger than lambda 2. And then to solve the optimum, we can solve it manually and obtain a closed form. But we don't want to do that. We want to write it in this form. And at the end, what we will obtain is that the first constraint is equivalent to U2 plus G2 larger than the max of all those things, subject to the constraint, which is equivalent to adding a vector of 6 variables here, and subject to those constraints, plus the other ones, lambda 1, lambda 2 here. So we can replace the first constraint by adding 6 variables and adding those 2 sets of constraints here. So we have here 1, 2, 3 equality constraints, non-negativity constraints, and 1 inequality constraint here. And we will need to do that for each of the constraints of our problem here. Yes, question?
Could you just quickly repeat why the lambdas, we have this equality?
This one?
Or no, above, between lambda 1, lambda 2.
This one?
Yeah, and then on the left side. Why do they all equalize?
This comes from the expression of the dual problem. Here I have a primal problem in lambda 1. Not in lambda 1, I had a problem in L1, L2, L3. I had this problem here. So forget about the left-hand side, just this. That's an optimization problem. My x variables of my optimization problem are L1, L2, L3. Right? So I wrote it in this form, maximizing AX subject to those constraints. Right? Sorry, minimize BY subject to those constraints. So this is what I did here. I did pattern matching in my catalog of linear problems, and I wrote the elements, which are what are my optimization variables, what is my vector B, what is my matrix B, what is my vector A. From that point, I'm working like a computer. I'm not trying to understand what I do. I just mechanically look from my catalog of dual problems. The dual of P1 is that one here. And the only trick I did, is because I will need to do it several times, so if I call everything X, I will have some confusion. So I call lambda apex 1 for the vector X of the dual variable. So this is exactly the same as that here. And this is where those constraints come. So they are constraints on the Lagrange multipliers, which of course are a bit harder to interpret. They can be interpreted in terms of marginal costs, but they are harder to interpret directly. And since we will have 60 or so different Lagrange multipliers, we may not want to look in detail at all of them. This is exactly, I'm just rewriting exactly the same constraint as before. The only thing I've done from the previous slide to this is I've replaced the objective function here of the minimizing problem as the right-hand side, which was the P star of u that I've given here. So thanks to this trick, I don't solve the optimization problem P star of u, but by adding up supplementary variables, I keep everything linear. And in compact form, this is what we obtain here. Other questions on this? So here's the recap. If I have a optimization problem, this is quite general. For us, it came naturally from an OPF with DC approximation and affine disturbance feedback. But quite generally, as soon as we have affine disturbance feedback, we will have this nasty term. And the classical technique to get rid of it is to use duality and add one set of dual variables for every constraint of this type, and the vector lambda 1 has the same dimension as this one here, the constraints, the right-hand side of the constraints on D, and there will be one per inequality here, and that gives this form here. Of course, there's a price to pay. Our original problem, when we have this, would require, if we want to keep the same number of variables, we need to solve the P star of u, which may be a difficult thing, may have a form that is nonlinear, so that will make the problem more complicated. It is certainly not a linear program of the dimensions of u. But here, we make it linear at the expense of having more variables here. So this is the technique we will use in the lab in particular. How many constraints do we have here? What's the value of J? J is the number of constraints we have where the disturbance appears here. So here we have to look where there is a blue and an inequality sign, and there is 1, 2, 3, 4, 5 times 2, because there's inequality in two directions. So the correct answer is 10. There are 10 variables here. And for each of the variable, we add one set of Lagrange multiplier, a vector lambda, which has the same dimension as C. Now what is C? What's the dimension of C? Any clue? Oh, let's stay with that. Well, C is the vector of is the number of constraints on D, on the disturbance. Now the disturbance is capital L. There are 6 constraints on L, 6 inequalities. Question?
Yes. We looked at the number of constraints. Why didn't take the first line in consideration with all the intervals?
This one?
Yes.
Well, because we look at the theory here. So the theory, there are two things. There are the constraints that involve U and D, such that for all D that satisfies something on D. Okay, so that's the first line. This one is the first line here. This one is the whole set here, excluding this constraint here does not involve the disturbance. So we have 5 lines, which gives 10 inequalities of this type. Capital J is 10, and this is a vector inequality. So implicitly here there are multiple inequalities here, as many as the dimension of C. And how many inequalities are there here? There are 6 inequalities here. So we obtain, if we use this formulation, every lambda j is a vector of dimension 6. So we add 60 variables for this simple example. This is what we need to do to solve this problem here. Let me skip a number of questions. Here is the result of the applying this to this example here. This is the optimal expected cost in red when I apply exactly here. So I'm not giving the value of U1 and V2, but I'm showing in contrast the value when I force V2 to be equal to 0. If I add the constraint V2 equal to 0, I'm doing exactly what we did an hour ago, which is the robust control without linear feedback. So we see two things. One is not very dramatic. We see that the cost is decreased slightly, not dramatically in this example. In other examples, it might be more dramatic. But more importantly, we see that the range over which the range of uncertainty on L3 over which this thing works is considerably larger. We double, in fact, the range of uncertainty where this system works. So we saw that before when we had an uncertainty of 50 megawatts on L or 100 megawatts on L, then it broke. The constant value of G2 was not able, you were not able to find one constant value that works for all cases. Here we are able to do that for a larger range. There's still an area where it breaks, but roughly speaking, you double the range here. Here are the values of V2. Here, V2 is the gain that we have here. And you see also the expected generation of G2, for example. We see that it changes as a function of the uncertainty of the load, which is typically why this problem was hard. The thing is non-monotonic somewhere in the optimal solution. This is why a simple solution that would work for all was not able to satisfy the problem here. That's pretty much it. Let's conclude by testing your duality skills. This is a problem we had seen last week, an optimization problem. It's a linear program. Which one is its dual? And the correct solution is B, I guess. So to know why, we go back to the catalog that we had before. So our problem is a problem of maximization with inequality constraint and non-negativity. So we go to our catalog, which is on Wikipedia or somewhere else here. A maximization problem with inequality constraint and non-negativity. So the dual will be a minimization problem with also inequality constraint and non-negativity here, so which will be problem B here. Let me conclude with the last quiz, which is a bit different, but with everything we have learned now about duality and optimization, we're able to do even more powerful things. So be careful here what it means. Here I'm proposing the following thing. Here I'm writing a sentence. The sentence is true or not depending on the values of A and B, because it's a sentence that has the quantifier for all x. It is saying my A and my B are such that for any x that satisfies those, we can think of them as feasibility condition of some optimization problem. Any x that is feasible for this must satisfy that. Cx is less than 3.14. So there is C also, and I'm saying that this sentence is true. So this sentence is true depending on the value of capital A, B, and C. Right? And I'm proposing three different statements. There exists lambda such that this inequality is true, lambda is non-negative, and this inequality is true here. Or for all lambda that satisfy this, it must also satisfy that. Or there exists y where this statement is true and this statement is true here, which, if any of those, are equivalent to that. And the correct answer is E. It's a bit more tricky, admittedly. Let's see why. So I think there's a typo here. The correct answer is E. Well, first there was a trick here. Obviously, this is the same as that. Right? When there is a quantifier, the variable is a dummy variable. You can call it whatever. The statements are the same. So this is the same as that here. Now, as we will see, this is the same as this. Why is it? Well, the condition is saying that if I consider the optimal solution of all the constraints here, maximizing this here, I'm saying there is one x. So the statement that we had was saying there is one x that satisfies the constraint such that Cx is less than 314. This is equivalent to saying that the max is less than 314. That's one of those tricks we've seen. Saying that an expression is less than a max means it is less than one of them here. So there exists an x is the equivalent to say that here. Now the dual here of this is given by those constraints, and the optimal value is the same here. So saying that the dual is less than 314, at least if this one is feasible, certainly the dual value is the same. And saying that the dual is less than 14 is saying that there is at least one feasible point that satisfies this here, which was statement A. So, admittedly, this is more contorted, but this shows the power of the techniques that we have just seen, that replacing quantifiers or constraint on something is larger than 1 by a min or a max, or something is less than all, also by a min or a max, is the classical technique we will use to solve many of the problems that always pop up when we are doing OPF with realistic constraints. Well, that's all for today. Quick recap. Handling uncertainties can be done either by minimizing expected or worst case costs. Very often we do expected cost. But the hard thing is usually to to handle the robust constraints. The constraint must be true with respect to all disturbances or with large probability when we do chance constraints. And the techniques to use that will invariably have to do with duality. This is why we spent some time in this course talking of duality. And then perhaps as a take-home message, which is more qualitative than quantitative, It is usually better to compute a policy than a set point. What's the difference between a policy and a set point? A policy is a rule that says if I observe this, I do that, which is typically what we do in a smart grid. In a non-smart grid, we do static thing. When we have a smart grid, that means we're able to observe the state of the grid, the state of the load, the state of the power injections. Then we can implement policies, which means systematic rules that decide what is the action, what is the control, once we have observed things. And we have seen in a simple example that, for example, a simple affine policy, which is the simplest of all policies, gives us something that is much more robust, is able to expand but double the range of uncertainties in which we will operate. Next week, we will see more efficient, or not more efficient, but more sophisticated ways of deriving policies when we talk about demand response. Voilà, that's all for today. We meet again on Friday with a little quiz on all this. For the quiz, the best preparation to the quiz is to redo all the quizzes that are in the slides and the quiz of the last year, and probably the quiz of this year will be in the convex set of that. Last year, quizzes are purely ticking boxes, which is perhaps not giving full credit to your intelligence. So this year there are also open-ended questions where I will ask you to, will not simply ask you to tick a box, but give the full solution. But the complexity will be at the same level of what you had to do in the quiz. For example, in the quiz of last year, I asked you what is the dual of this, and then you have to choose between 4 duals. This year I might ask you, write the dual instead of choosing it. Voilà, thank you very much. Bon courage.